We are back once again. This is day 36, the LeetCode Everyday Grind. Make sure to join the Discord, it's the Hyperbolic Coding Chamber. We have 3 problems set up. We have evaluate, evaluate reverse Polish notation, course set, course schedule, implement trie. We're going to try our best on these problems, but I've already heard from the copy ninja himself that course schedule is an impossible problem and it's never been solved. And I don't even know what a trie is. I think it has something to do with storing a string as a binary tree, but we'll try that. And then we'll try evaluate reverse Polish notation. So we have 2 hours on the clock. So I'm just going to jump into it with, I'm just going to jump into it, and we're going to start with reverse Polish notation. So now we can just jump into it. Evaluate the value of an arithmetic expression in reverse Polish notation. Valid operators are plus, minus, star, and slash. Each operand may be an integer or another expression. Note that the division between two integers should truncate towards 0. It's an interesting thing to mention. It is guaranteed that the given reverse Polish notation expression is always valid. That means the expression would always evaluate to a result, and there will not be any division by 0 operation. So interesting enough, so we have reverse Polish notation. Let's see what that means. Also known as reverse Polish postfix, or simply postfix notation, in which operators follow operands. Interesting. I think we can see that we have 2 plus 1, 2, 1, and then plus. So they want us to add 2 and 1, right? And then this entire set would be a operand, and then we'd have 3, which would be a operand, then we'd have the operator. So we have 4, 13, right? But first we have to do 4, 13, 5. So basically we have 13, 5, right? Divided by 13 divided by 5, and then that plus 4. So that is interesting. So we have another one. So I have 10, 6, 9, right? And then I have 6, 9, 3, and then 9, 3 plus. So we know we have 9 plus 3, right? And then we have that times 11, right? And then we have that. Interesting. So I'm thinking of some ideas right now. The first one, I'm thinking of visualizing the array of strings as a binary tree, and if we imagine it, then the third node would be the top node. Maybe we'd have 2 and 1, and then the top node we'd have times here. So I'm not really seeing how visualizing as a binary tree makes sense, so maybe that is not the best way to go about it. What if we try something stack related? So what if we push 2 onto a stack, 1 onto a stack, and then we have plus. So now we want to evaluate. We have plus times 2 plus 1, right? And then we'd have a value in the stack, which would be 3. Then we'd push 3 onto the stack, and then an operand onto the stack. And since we have an operand, we'd want to evaluate what's left in the stack. So that makes sense. For example 1. So right now it looks like maybe the best thing we can do is keep a stack. And we'll have 4, push that onto the stack, 13, push that onto the stack, right? And then we'll have 5, but then we'll apply division due to the current operator with the current operator with the last two elements pushed onto the stack. And then we can do plus, which will also operate on the remaining two elements. So if we do on the example 3, we could do 10, 6, 9, 3 plus, evaluate these two, right? Negative 11, then star, right? And then we'll do 12 times negative 11, right? So that is what they want. And then from there, we'd have another output, which we would divide by 6. So I'm thinking that this does make sense. And so we'll keep a stack and iterate through the tokens, right? And if token is an operator, right, then we want to perform the operation. Otherwise, push on to stack. So how do we perform the operation? Well, the operation would simply be the current element on the top of the stack and the element before it, and performing the operation. And so we can have a function to perform the operation. So let's try that. And there's always at least one token. Tokens of I is either an operator or an integer in the range, but we could be given, so we have some edge cases where, let's just say the given token, right, since it can be plus, minus, star, or divide, maybe none of those values, maybe the one value in the token array is an operator. So handle when token op is only operators. But for the general algorithm to start, we could say const stack equals an array, right? We want to iterate through the tokens, so we could say for const token of tokens, right? And we'll say if token is an operator. How can we know if it's an operator? We can create a map of operators, so we'll say operators, and it'll actually just be a set, right? And from this set, we can just create a set from this array of operators, and the operators are multiplication, plus, minus, and division. And so say if token is an operator, so if operators dot has token, then we have an operator, right? And we want to do something with it, right? Else we want to push it must be an operand, so we want to push it onto the stack. Let's say stack dot push, and since it's an array of strings, we're gonna have to cast that token, right, to the integer. And we actually don't know that all the values will be integers, so let's just say parse float. So we'll push it onto the stack, and if it is indeed an operator, so we have operators that has token, then we want to perform the operation. So the operand op1 is going to be so we actually have to, so we can't actually have 2, right, and then plus, because that would not give us all the operands before the operator. So op1 would be stack dot length minus 2, and op2 would be stack dot length minus 1, and we basically actually can just pop them both off the stack instead of actually getting them. So we just say stack dot pop, and then we'll say the value, right? We can create const value equals form operation, and we'll have op1, op2, and the token, which is the operator. So P will have this function form operation, and we'll have op1, which can be a number, op2, which can also be a number, and operator, which is going to be a string, and all of this is going to return a number. So from here we can say if operator equals star, right, and return op1 plus, if it's a star, right, op1 times op2, else if operator equals minus, right, return op1 minus op2, right, else if operator equals minus, operator equals division, right, we'll return op1 divided by op2, else the remaining one can only be plus, so we'll do op1 plus op2. So from the operation, then we'll push that onto the stack. And then at the end, we should just be able to return the last element in the stack, which should be stack sub stack.length minus 1. But granted, we still have to handle the edge cases, but let's see if this makes sense. Oops, so we didn't push the value onto the stack. So what's happening is we added 4, we added 13, we added 5, then we got division, so we should have did 13 divided by 5, which gives us a particular value, which we multiply. So 13 divided by 5 should be 2.2, right? And then we'll have another operator, so we should have gotten 2 plus 4 to give us 6. So somehow we're only getting 4, and I'm just going to print the stack at the end to make sure I'm following for this particular example. So we have 4.384. We do have op1 divided by op2 minus and star, else we return op1 plus op2. And so what if we return value? What if we print value as we're going through? So now we're getting 0.384. So let's check our ops. So we have 5, 13, and 0.38, which is interesting. Okay, I think I see what's happening. We pulled these off. So when we push, so when we push the value, right, we push the value onto the float, onto the stack, right, it has to be an actual usable value. What we return from value, what we return from form operation is a number. But what we need to do is make sure that, right, actually if we're popping these off, they must already be, if we're popping these off, they must already be numbers. So they are numbers. So we have 5, 13, and our solution, we get, which is 4.38. So something's wrong with the algorithm here. So let's just follow it through. So we have a token of tokens, right? We add 4 if operator has token. Well, we don't have, 4 is not an operator. So we push the parse flow to the token, which is 4. Then we go to 13. Well, 13 is not an operator, so we push 13 on, right? Then we go to 5. Well, 5 is not an operator, so we push 5 on. Then we get division. So then we pop off 5 and 13 from the stack. We have op1 and op2, and we have the token, which is indeed an operator. We do 13 divided by 5. So 13 divided by 5. Oh, I think we have to swap them actually, because we're doing 5 divided by 13. And I think this is the only operation where that matters, because the rest are commutative. And it looks like we're actually supposed to return an integer. Output is rounded up. So maybe maybe we take the floor. It doesn't specify whether all our inputs should be treated as integers or not. So here we're getting 12. I think I see what we're saying. Here we're getting 12 somehow, when the answer is supposed to be 22. So all these are commutative except division. So I actually don't think we have to swap these here. All we have to do is swap them here. So we'll test for our original case again. We still end up with 6.6. So I'm wondering, division between two integers should truncate towards 0. So I think we are supposed to floor it. So it's guaranteed it's always valid. And it also seems right. In this case, subtraction also has that property as well. Now we're going to want to pull the operators in the correct order. So 10, 6, 9, 3. 9 plus 3 is 12. Right? 12 times negative 11 is negative 122. Somehow we're getting 12. Pushing the parse float of the token. Maybe it's possible that we're out of tokens, but we still have things we need to process. So what we could actually do is at the end, well, let's see, right? We're printing the stack, right? At the end, the stack is actually 12, so there's nothing left remaining in the stack. So the output is indeed 12, expected 22. To perform op1 and 2, so there must be something wrong about our method. Back to the original problem, we had 10, 6, and 9. So here we have 17 plus 5, and maybe that's where no, we seem to be good there, because it's interesting. Maybe we can actually check on each iteration. Every time we pull value, you would just print it. But we wanted for that specific test case that was failing. So we have 12, right? And then we can actually compare this with what's happening here. So you have 12, right? And then we multiply by negative 132, right? And then we divide it by 6, and you definitely don't get 1. So let's just, I was avoiding actually working through the problem. It seems unavoidable. Let's try 10, 6, 9, 3. So we do 9 and 3, right? And we can just copy this and work through it really quickly and see where our intuition is failing. So you have 6, 9, 3, iterating through the string, right? These two concatenate to become 12. We have negative 11 times 12 times negative 11. This becomes negative 132. Negative 132 divided by 6. Negative 132 divided by 6 should be 22. Somehow we're getting negative 1. Somehow we're getting negative 1. So we have so maybe we'll just print op1, op2, and the token and what we got. So then we'll just see what sequence of operations doesn't make sense. So 3 plus 9 is 12, negative 11 plus 12 equals negative 132. Negative 132 divided by 6 does not give you negative 1. So if we have negative 130 divided by 6, that should give you negative 22. Somehow we're getting negative 1. So something wrong with our perform op for this division. We're doing op2. So op1 is negative 132, op2 is 6. So when we flip them, we're doing op1, which is 6 divided by negative 132. So now we're getting negative 22, which is correct. So you get negative 22, right? Negative 22, and then you would have multiplied it by 10. No, 6 divided by negative 132. So maybe we should be flipping them. So you're getting negative 1 before, but what it should actually be is 0. $32. They want 6 divided by, which is indeed giving us negative 1. We want it to be 0. What if we don't floor it? Let's see what we get here. So if you don't floor, you get negative 0.14. I guess when you floor a negative number, it goes to negative 1. So here our answer is 7. So here our answer is 7. So this is a case in which we would like our answer floored. Or not that we want it floored. We basically want it to be an integer There's more cases where, depending on the value, it's unclear whether we should be going upwards or downwards. Maybe what we should be doing is we'll do the parse int. So the value that we push on is always truncated towards 0. I see. So this makes sense. There was just a lot of smaller things that were messing me up. The reverse Polish notation, the intuition is that we keep pushing elements onto the stack until we reach an operator, then we pop the last 2 operands off the stack and process it. Now I'm wondering if we even need this parse int part, so now we're fixing the input. So we're still good there, and it's still pretty quick, so let's check the solution. I mean, the time complexity, this would be linear time with linear space, because at worst we have to keep a stack or a linear data structure that has the ability to store the operands, so that we can process them. Note that the input type is an array of strings, not an array of cards. So you should be comparing them with dot equals and not equal equal. On LeetCode, this is probably why there's a bug in your code, not in the LeetCode platform. Some programming languages do not truncate towards 0 with division, so you need to figure out how to make them do so. Example, if we put negative 121 divided by 7 into Python, we get 18, but we actually wanted negative 17. If unsure about your programming language, either check the documentation or simply write a program that does negative 121 divided by 7 and see which result you get. If you put numbers around the correct way, test case 12, 7 minus means you should calculate 12 minus 7 equals 5, not 7 minus 12 equals negative 5. This is because addition, multiplication are commutative, which means the order of the operations doesn't matter. If you aren't certain you have it right, try this test and check whether you get 5 or negative 5. Try to understand how reverse Polish notation works and then design an algorithm yourself rather than following the provided pseudocode too closely. What it means for integer division to truncate towards 0, then at what reverse Polish notation is. If you're to skip these sections, if you already know this stuff. Early on in your programming career, you probably learned about integer division. When dividing 2 positive integers, we always truncate down to the nearest integer. The non-integer values are in parentheses after reference. The most programming languages do integer division by default, as opposed to float division, where decimal places are kept, and this is how they handle positive integers. Both of the following definitions could be and are used to describe the truncation. The result is truncated to a less than or equal number. 1 is less than 1.8. The truncation is towards 0. 1 is closer to 0. 1 is closer to 0 than 1.8 is. For negative numbers, however, it is impossible to satisfy both of these. So one or the other has to be picked. For example, negative 9 divided by 5 equals negative 1.8. If we wanted the truncated result to be smaller, we'd have to go to 2. Negative 2 is less than negative 1. If we wanted the truncated result to be nearer to 0, we'd have to go to negative 1, as negative 1 is nearer to 0 than negative 2 is. Some programming languages go with the first definition, others go with the second. For this problem, you're expected to go with the second definition, regardless of what your chosen programming language uses. Doing the division, luckily the int function does truncate towards 0, and therefore we can use int a divided by b trick. But this is not the same as int a / b. We haven't checked what all the programming languages available on LeetCode do. Great context for understanding reverse Polish notation. Also, we know how to read expressions written using infix notation. Valuing the following expression is something you've learned to do in elementary school. This isn't too difficult. Many of you also have seen viral posts circulating on social media websites such as Facebook that challenge you to evaluate an expression like this. Check the comments on many of the other strings answers. You'll probably see people arguing about the answer is 10, 27. The reason for this disagreement is because different people have different understandings about how such an expression is evaluated. Those who say the answer is 10 is evaluated strictly from left to right, the following steps. Those who say the answer is 27 follow rule or common misunderstanding of the widely used mnemonics PEMDAS, BODMAS, and BEDMAS. Steps of this method are as follows. Do division first, multiplication, addition third, subtraction. Now please use the rules most programming languages use, and that is also the correct implementation of the mnemonics PEMDAS. That is to do division, multiplication first in order from left to right, and then addition and subtraction in order from left to right. So evaluate with stack should be linear time. Where the total cost is proportional to the length of the input array. Unlike before, we're no longer doing expensive deletes from the middle of an array or list. Space complexity would be linear space as well. Interesting. So now we'll try course schedule. So we have course schedule. There are a total of num courses you have to take, labeled from 0 to num courses -1. You were given an array prerequisites where prerequisites of I equals a tuple. Indicates that you must take course BI first if you want to take course AI. Okay, for example, the pair 0 and 1 indicates that to take course 0, you first have to take course 1. Return true if you can finish all courses, otherwise return false. So here we have num courses 2. So there are a total number of courses you have to take, labeled from 0 to num courses -1. You're given an array prerequisites where prerequisites of I equals AI. BI indicates that you must take course BI, so you take course 0 before we can take course 1. So the pair 0, 1 indicates that to take course 0, you have to take course 1. Return true if you can finish all courses. Otherwise, return false. There are a total of 2 courses to take. Take course 1, you should have finished course 0. So it is possible. Num courses equals 2. Prerequisites are 1, 0, and 0, 1. So there are a total of 2 courses to take. Take course 1, you should have finished course 0, and to take course 0, you should have finished course 1. So it is impossible. So in a weird way, I'm thinking that num courses goes up to 1 to 2000. So I think does num courses equal the length of the prerequisites array? I.length equals 2. Num courses is less than or equal to a sub I and b are greater than or are greater than 0 or less than num courses. So I'm not quite understanding exactly the role that num courses plays. So a total of 2 courses to take. Right, to take course 1, you should have finished course 0, so it is possible. There are a total of 2 courses to take, so when num courses equals 2, we still have 2 different numbers and 2 different amounts of elements in the prerequisites matrix. Take course 1, you should have finished course 0. And to take course 0, you should have also finished course 1, so it is impossible. So what I'm thinking here return true if you can finish all courses. So there are a total number of courses you have to take labeled from 0 to num courses minus 1. Okay, so labeled to num courses minus 1. So the courses we have to take would be 0 and 1. And the courses we have to take here are 0 and 1 as well. I see. So num courses is also the courses themselves, because these are the labels. They're just labeled with integers. So what I'm thinking is that we can kind of view this prerequisites matrix almost like an adjacency list, except each we'll need, or we're given a matrix, but we need to turn it into an adjacency list. And if we can turn, maybe if we can turn prerequisites into an adjacency list, then we can just can figure out if prerequisites has a cycle. And if it has a cycle or a loop, that means it's not possible. So to do that, we'd first have to figure out courses we're interested in, right? And to get prerequisites into an adjacency list, you can iterate over prerequisites over prereqs, check if, iterate over prereqs, and then we could check if we iterate over prereqs, and we're basically just going to load the particular course, right, which is 1, and its required course, right? So it's going to map a course to required course, right? And so we're iterate over prereqs, right? And if prereq sub 0 in interested courses, right, because we want the course we're interested in, then we'll add it to our map. And so this map, in this case, might look something like 1 goes to 0, right? And so when we try to figure out if the prerequisite has a cycle, we just have to iterate over all the keys in the map. So we'll say 1, right? And then we'll go to 0, and we'll check the value. If we haven't seen the value yet, is that a way we could check if there's a cycle? We want to, so we have the map, which is going to be our adjacency list, but we're also going to need a set, right, for visited, right? So if we go over the first key, right, we visit the first key, right, we set add it to visited, right, so visited equals 1, right, and then we're done. We can actually return true. So let's try it with the second example where that's not the case. So we'll visit course 1, right, check its neighbor, and its neighbor will actually be 0. I mean, not its neighbor, its neighbors. If it's an adjacency list, its neighbors will be 0. So we'll add its neighbors to the visited, right? But on the next version, we'll check the key, right, which is the course, and this works because I think they said the courses are unique. We check if 0 is already in visited, and it is, so it wouldn't be possible. We would return false. So at the end, we can return true. So I think we could do this, but first we have to generate the interested courses. So const interested courses, and we can get this in linear time, basically. It's an array. What we'll do is let I equals 0, and we'll say, well, I is less than num courses minus 1, I plus plus. We'll do interested courses dot push, and we could even make it a set just to make it faster. We're just gonna push I. Now we figured out the courses. So now we need to figure out the courses we're interested in. So we figured out the courses that we're interested in. Now we need to get the prereqs into an adjacency list. But only the courses that we're interested in. So we do for const prereq of prerequisites, right? And we could either do course, right, and requirement, and then we'll have a map or adjacency list, right? And this map is going to be of type number to number. I guess another question is, can a course have multiple prerequisites? This is all the pairs of prerequisites of I are unique. So we'd say adj.set, right, the course to its requirement. So we have that. Now so we want to put prerequisites into an adjacency list. We should have wrote better pseudocode. If we put prerequisites into an adjacency list, we'd basically have 1 to 0 and 0 to 1. Right now you want to iterate over prereqs, and if prereqs of 0 is in interested courses, so maybe we only create an adjacency list of the courses we're actually interested in. So we'll say if interested courses dot has course and this is a course that we're interested in, right? And I don't think we need to iterate over prereqs here. Now we can just, since we have the adjacency list, right, we just need to check if there's a cycle. So we'll need a set for, call it visited. It's going to be a new set. It's going to be a new set, and we're going to iterate over the map, right? So say const course and rec of the adjacency list, right? We're going to say, hey, if visited dot has course, right, then we're going to return false, right? Else we're going to add it to visited. Actually, I think we could just do it like this for the pair. Say pair dot for each course, right? And we'll say if visited has course, then return false. Otherwise, right, we want to add visited, add it to the course. I mean, add it to visited because we visited this course. And then we should be able to return true. So let's see if this makes sense with the first example. So it works so far. Okay, so we fail here. We have the courses we're interested in, and we return true. So if 1, so we iterate through our map, and our map should be interested in 0 and 1. So we visit 1 and the pair, so 1 and 0, right? And if we check for 0, right, it should be in visited. So actually let us check the adjacency list on this particular run. So our map only has 0 to 1. Our adjacency list only has 0 to 1 for some reason. Interesting. So our adjacency list isn't complete for some reason. So let's check if interested courses has all the requirements. It should have 0 and 1 in it. So it doesn't, it only has 0 in it. So we have so what we really wanted was num courses, or what we had earlier with an inclusive end. 0, so we have 1 maps to 0 and 0 maps to 1. So then for the pair, so we'll print the pair. So for the pair, if visited.has course, which visited should, so it should have 1 and 0 in it, but it's for the pair, so for each in the pair, right, if our set has 1 and 0, so if visited has course, you return false. And what I'm guessing is, because of the way this for each works, it might be a little strange. So if we just do for const course of pair like this, then I think we should be good. So a bit of a closure problem there with returning value. So an even bigger problem, we return false. So you need to, to do one, you need to visit, to do one, take course 1, you need to take course 4. But what if course 4 doesn't exist? I see, we can see this in our map, right? Course 4 doesn't exist. So our iterating through, we can say if visited has course, right? Or if the adjacency list, right, of our interested courses, right, if it doesn't have the course itself, right, then we definitely want to return false because it wouldn't be possible. Oh, wait, they're saying it's true. The expected output is true. So to take course 1, you have to take course 4. Okay. And to take course 2, you have to take course 4. Take course 3, you have to take course 1. And then to take course 3, you also have to take course 2. I see. So you can have multiple courses as a requirement. So if that's the case, all we have to do is change our adjacency list to its real representation, which is really an array. And what we'll do is we'll say if interested courses that has course, then we'll want to get the array, say adj.get for the course, right? And so what we'll say is, right, if this exists, or if adj.has course, right, then adj.get the value, get the array, otherwise create a new array, create an empty array, right, and we'll push the course onto the array, then we'll set course equal to the array of required courses. And then from here, instead of doing for const course of pairs, you can create relevant courses, right, which will be pairs of 0, but then pairs of 1, right? All of these spread into the array. All of the neighbors spread into as something we'd like to visit, and then for const course of relevant courses. And then we don't have to do this thing where we don't need visited either. So to take course 3, you should have to take course 1 and 2, but our map is saying 3 and 3. And it's because we're pushing the course. What we would like to do is push the requirement. So that is good. And then we're actually returning false still. So let's just check that. A lot of console.logs. So we'll remove the extra logging. Then we'll have this mapping here, and we want to return true because we would go from take course 1, you have to take course 4, right? To take course 4, take course 2, you have to take course 4, take course 3, you have to take course 1, and then to take course 3, you have to take course 2. The way the algorithm currently works, we take the first pair, which is the course, right? So we say 1, right, and 4, and we'll say if visit doesn't have course, which it doesn't, right, we'll add the course. So we add 1 and 4 to visited. Then we go to 2 and we say, all right, let's add 2 and 4. Oh no, let's add 2 and 4 to visited. right, before it's already in visited, but even if we got to the end, right, with 3, 1 and 2 is already in visited, and they want us to return true. So maybe it's not that it has a cycle, probably misunderstood the problem. So the prerequisites are 1, 0, and 0, 1. There are total of 2 courses to take. Take course 1, you should have finished course 0. And take course 0, you should have finished course 1. So maybe what we could do is we could say, all right, well, so maybe we'll only add the courses that we want to take. So if we only add the courses we want to take, we'd add 1, then go to 2 and add 2, then go to 3 and add 3, so we'd return true. But then, right, we want to return false, right? So if we only add 1, we add 0, right, then it doesn't exactly work, since our current version doesn't exactly work. So maybe we want to check if we've taken course 1, we need course 0, so then we get to 0, but it says we have to take course 1. So my premise was that if we've revisited the same node, then if we revisit the same node, because we're pretty much drawing a graph, if we revisited the same node, then it should be impossible. But maybe we only want to say we visited it. So first node, maybe it's when a prereq, when we have a problem, it's when a prereq is a course, when a prereq, right, which is a prereq, which are a course we want to take, and we have a prereq. The problem is when we have a course we want to take, which is also a prereq. So if we go to 0, 0 is a course we want to take, but it's also a prereq. So maybe that's how we could do it. We could say courses, right? And then we could also have prereqs. And it seems to be when course you want to take is also a prereq for another. So so we want to do, I think, instead, you do if courses so when a course you want to take, which is 0, is also a prereq for another. So it's looking like maybe all we really need is the prereqs. So we could say const prereq equals pair sub 1. This would be multiple. And we could say for const prereq of prereqs, right? And whenever if prereqs has if it's already a prerequisite for another course, you want to return false. Otherwise, you want to add prereq add prereq. So in this case, right, we go to visit 1, we only add 0, right? And in this case, we still return true. We visit 1, we add 0, but then it's actually that the course we want to take, so it actually would be pair sub 0. No, I guess it's double, right? Because we want to add all the prereqs. Right, so this is actually fine. We actually don't want to return false here. What we want to add is all the prereqs to the prerequisite array. But before we do that, we can just do it like this. We'll say course prereqs. Before we do that, we'll say if prereqs.has course, which means the course we want to take is a prerequisite for another course. Then we want to return false, otherwise we can load our prereqs in. Property has does not exist on type number. Oh, so we're overshadowing here. So we'll just call this visited, and we can remove courses. So let's see if this makes sense. So we fail here, and we're supposed to return true. So we want to take course 2, right? We have to take course 1. But to take course 1, to take course 1, but to take course 1, you have to take course 0. So I don't think we're actually, it's when a course you want to take is always already, when the course you want to take, so if we go back to our 0 example, the course we want to take is also in the courses array, which requires a, so we were right the first time, courses visited, so it's if we have prereqs visited, prereqs visited dot add. So it's when a course we want to take, right? So prereqs dot has 0, and it would, but also one of our prereqs is already in the course. So say and prereqs dot sum p, right? We'll say courses visited dot has p. So if prereqs dot visited has course, right, which it will, and if any of our prereqs, which is 1, exists in the courses array. And to do that, we're also going to need to add courses visited dot add course. So we return true here. It's not possible. We have 0, 10, take course here, take course 10. 10 doesn't exist. So maybe we also want the case where if the course doesn't exist, you can't take it. Right. So we'll wrap this in a big loop, and we'll say one of these, right? So if the course we need to take, if any of our prereqs don't exist, so prereq exists if prereqs dot sum, right, p, right, if the adjacency list technically only puts courses we're interested in. But if the adjacency list has, if the prereq exists, I'll say if the prereq doesn't exist, right, then you definitely want to return false. And it looks like our final case is when one, of course we're interested are 0 and 1. What we return is here we could have and I think it says that if all the pair prerequisites are unique, so I think we can just say if prerequisites length is 1, then return true. So basically you just have to copy this So I think our solution is just not optimal. The way this works, we keep running into more and more cases. You want to take course 1, but it requires course 4. Course 4 doesn't exist, so we return false, right? But at the same time, now it seems that that's okay. Maybe it's not because of course 4, maybe it's because you have to take course 3, you have to take course 1, take course 3, you also have to take course 2. This still returns true, but technically it's false. So if we have this adjacency list and we're basically checking if, I don't know if we understand the rules correctly, since we have 1 and 0. Oh, so the problem is equal to finding if cycle exists on a directed graph. If cycle exists, no topological order exists. So that's what we're doing. So we said in the beginning, but still we're unable to locate the solution. The reason we're failing on this submission is because maybe we're interested in the courses 0 through 4. Is that inclusive? From 0 to num courses minus 1. So it looks like we are interested in it. Take course 2, you have to take course 4. Take course 3, you have to take course 1. And so you should be fine. But if I remove my prerequisite exists, then we fail in another case. So I guess the question is, when do we want to make sure that the prerequisite exists? Then we get lost on this one because node 10 doesn't exist, but we would be interested in it because we're interested in courses 0 through 19. But we are expected to return false here. So we would do if prereq, maybe the case is if prereq doesn't exist and the prereq so the adjacency list has the prerequisite and interested courses has P as well. And if we say no, so if the adjacency list has P, right, and interested courses doesn't have P, so prereqs, right, if the adjacency of this list has P, it would have 10. But is 10 in our interested courses? It is. So if this is true, we need to change this to or. Then we'll check on this case. So we just have another case. To take course 1, you have to take course 4. But we just had to include num courses up here. Do num courses minus 1. Take course 1, you have to take course 4. Course 4 doesn't exist. Or maybe course 4 does exist. No, course 4 does not exist. So we still return false. So course 4 doesn't exist. Now we have the course and the prerequisites. So I think we should just check the solution. The problem can be modeled as yet another graph traversal problem. So the vertex in a graph and the dependency between two courses can be modeled as a directed edge between two vertexes. So we did, and the problem to determine if one could build a valid schedule of courses satisfies all dependencies, the equivalent to determining if the corresponding graph is a directed acyclic graph. There is no cycle existing in the graph. Typical strategy for graph traversal problems would be backtracking or simply depth first search. Here, let us start with the backtracking algorithm, which arguably might be more intuitive. As a reminder, backtracking is a general algorithm that is often applied to solve the constraint satisfaction problems, which incrementally builds candidates to the solutions and abandons a candidate. Backtracks as soon as it determines that candidate would not lead to a valid solution. General idea here is that we could enumerate each course vertex to check if it could form a cyclic dependencies. Starting from this course, check of cyclic dependencies for each course can be done via backtracking. We incrementally follow the dependencies until either there is no more dependency or we come across a previously visited course along the path. The overall structure of the algorithm is simple, which consists of 3 main steps. Step 1, we build a graph data structure from the given list of course dependencies. Here we adopt the adjacency list data structure as shown below to represent the graph, which can be implemented via hash map or dictionary. Each entry in the adjacency list represents a node, which consists of a node index and a list of neighbors at nodes that follow from the node. Step 2, we then enumerate each node course in the constructed graph, check if we could form a dependency cycle starting from the node. Step 3, we perform a cyclic check via backtracking, where we breadcrumb our path, mark nodes we visited to detect if we come across a previously visited node. Also remove the breadcrumbs for each iteration. So 0, 2, 1, 0, loop detected. This approach is included because it is an intuitive starting point and it will provide a better understanding for the following approaches. Due to its time complexity, it is not expected to pass all test cases. Complexity, absolute value of E plus vertices squared, where E is the number of dependencies, V is the number of courses, and D is the maximum length of acyclic paths in the graph. First of all, I would take its absolute value for the graph in the first step. For a single round of backtracking, in the worst case where the nodes chained up in a line, it take us maximum V steps to determine backtracking. Post order. As one might notice that with the above backtracking algorithm, we would visit certain nodes multiple times, which is not the most efficient way. For instance, in the above graph, the nodes are chained up in a line. The backtracking algorithm would end up being a nested two-level iteration of the nodes, which we could rewrite as the following pseudocode. Nodes or chain range island. The answer is yes. The first node in the chain, once we've done the check that there will be no cycle formed from starting from this node, we don't have to do the same check for all the nodes in the downstream. From the perspective of graphic traversal, the above rationale could be implemented with the strategy of post order. In which strategy we visit nodes descendant nodes before the nodes itself. We implement a post order DFS based on the above backtracking algorithm by simply adding another bitmap, which indicates whether we have done the cyclic check starting from a particular node. Here are the breakdowns for the algorithm, where the first two steps are the same as the previous backtracking algorithm. We then enumerate each node course in the constructed graph to check if we could form a dependency cycle starting from the node. Check if we could form a dependency cycle starting from the node. We check cur course stick checked path is cyclic. This node has been checked. No cycle will be formed with this node. Turn false if path cur course came across a marked node in the path, cyclic. Post order, DFS on the children nodes mark the node in the path. Post order to visit all its children first. In course stick, self is cyclic child course checked path. After the visits of children, we come back to process the node itself. Topological sort problem is to find a global order for all nodes in a directed acyclic graph with regard to their dependencies. Linear algorithm was first provided with a canon. Topological order, if there is any, here we quote the pseudocode of Kahn's algorithm. Interesting. So I'm not really seeing exactly where we went wrong. So we build the graph, except, right, we ended up doing the same with building the adjacency list. But for the current course in the range num courses, these are the courses we want to check if they're cyclic. Cur course and course dict. So if path came across a previously visited node, right, return true. Before backtracking, mark the node in the path. Right, for child in course dict is cyclic. Interesting. So I have to give this another shot. Let's try. Implement trie. A trie, pronounced as trie, or prefix tree, is a data structure used to efficiently store and retrieve keys in a data set of strings. There are various applications of this data structure, such as autocomplete and spell checker. Implement the trie class. Initialize the trie object, void insert, string word inserts the string word into the trie. Boolean search string word returns true if the string word is in the trie, and false otherwise. Boolean starts with returns true if there is a previously inserted string that has the prefix. Otherwise, so trie would insert a string, right? We'd have apple, right? Search for apple, return true. We'd have app. Search for app, we return false. Starts with app, true because apple starts with app. Insert app, and then search app. So we should return true. The word length is 1 up to 2,000. Word and prefix consist of only lowercase English letters. Most 3 times 10 to the 4 calls in total we made to insert, search, and starts with. So a prefix tree is a data structure. Additionally, store and retrieve keys in a data set of strings. If that is the case, maybe a child can have maybe a particular node. So this would be the so this would be the data structure itself, which would be a prefix tree. So maybe we can represent this as a tree, but more than a binary tree, we could call it an n-ary tree. N-ary tree, where each node has 26 children. To do that, we could create n-ary tree, and it would have the constructor plus some properties. The properties it would have would be value, which would be a string, which would be set to nothing to start, and we would end up creating n-ary trees for its children. So we could say the way it connects to other nodes is by a children, right? And these children would also be n-ary trees. So this would be an array, right? And so we're going to basically do a for loop, right, from let I equals 0 all the way up to 26, and we do I plus plus. We're basically going to say that let's start equals a dot car code at 0, and we're going to do children dot push children dot push. We want to create an n-ary tree, right? And the most it can really take is a value, right, which is going to be a string. Going to be a value. Actually, no, we're going to set this dot value equals value, and then we just want to create a bunch of empty n-ary tree children. And so the goal would be to be able to represent a tree node with 26 children and be able to instantly index those children to see what nodes also relate to those children. To do children not push n-ary tree, they would all be empty. And then we would have in our class, right, root, which would be an n-ary tree. And we want to insert a word into this tree, right? Just to start, we should run this and just with some basic values just to see if our tree is being created correctly. And we're supposed to actually have this dot children, and this should be this dot root. And we also need new to create that new instance. We want to class. We want to set this equal to an array. That is interesting. We actually don't need a value to start, but this dot children dot push new n-ary tree. Oh, and each one creates. Okay, I see what's happening. So maybe the goal is to simply have a empty array. Right, and when we insert a word, right, when we insert a word, then we actually want to pass through and create these things. But we do, I think we do in the end want those 26 indices just so we have access to them. So we'll just say null, null, null. I don't know if this will still exceed the call stack. So we're fine here. So this works. So when we insert a value, right, we're starting at the root, and we basically want to do depth first search, right? And so I think what we want to do is we want to insert, right? Maybe we could use insert as the staging for our recursive function, right? We'll say if word, right, sub 0. So if that exists, right, then what are we going to want to do? We're going to want to do, actually, we can actually also do const lc, right, or dot to lowercase. And then we'll say if LC sub 0, right, exists, then what we're going to want to do is we're going to have access to and maybe this actually won't work very perfectly. So basically what we want to do is, if we know that this value, this first value in the string exists, so we want to add an apple, we want to check if the current node, right, but the current, we can't really use this because we need to do different versions, so maybe we'll create a function called Dfs Insert word string, right, void, say if LC dot sub 0 exists, do Dfs Insert, right, and we'll start with root and go to word, right, to lowercase. So if that value exists, right, which it does, and I think it's actually just if word exists, we want to call it Dfs Insert, and the goal here, right, is we're going to have a node, right, which is going to be an n-ary. We couldn't have to call it n-ary tree, we could have called it n-ary node, right, or a word. We're basically going to do the same check. We're going to say if word, right, sub 0 dot exists, and we want to, where we currently are, right, we want to say if node, right, and we can get the index, right, index is going to be the word, right, which is the first letter in the word, and we want to translate it to an index, so it's going to be a, or whatever the character is, lowercase, right, but let's say dot, we don't have to do this because we know the value exists, we'll say sub 0 dot car code at 0, right, minus, I think, 64. And then we'll just print index to make sure we're on the right track here. Ideally, this would print, we have to say this, Dfs Insert word index. This dot root, standard out is 33. So what is the word that we put in? The word that they're putting in is apple, right? And so the IDX is 33, which I think means we're slightly off. So actually print word sub 0, right, and word sub 0 dot car code at 0 and the index. So it's A, right? The car code is 97, and so lowercase a, it seems actually starts much higher. So we actually want to do minus 97. So that actually works out perfect. And then here we can say, right, if node sub index, right, then what we want to do is create that value. Is go to the next value, right? So we call Dfs Insert again with word dot slice 1 going to word dot length. Or we'll do it like this, which I think substring and substir are slightly different. So we'll go from 1 to word dot length, right, and pass in node sub index. And then we'll just print the word to make sure that this makes sense. So we don't want to print the root anymore. We have apple, and then we have app. So it's not exactly what we want. We start with the root with the word going to lowercase. Then in our next call, you get the index of that letter, right? And it exists. And you want to take, maybe it's substring, right? You want to take, starting from that index 1 and going to word.length, but we get app. So maybe I'll just actually do it right here. We'll say 1 word.length to see what we get. So I think this slice should work, but the fact that it's returning PP is a little concerning. We do word.substring, right, starting at this index. We pretty much want to just delete the last character. I mean, delete the first character. So we might need a variable const shorter could be equal to word.substring 1, right, going to word.length. Value would probably be shorter, right, and we want to use shorter. Otherwise, right, we want to create, we want to set the value at this index, right, equal to a new n-ary tree, right, where the value equals word sub 0. And now I'm realizing that we pretty much want this to run. This DFS portion we kind of always want to run. So if the node exists, then we're going to depth first search. So if the node exists and shorter.length does not equal 0, right, then you want to recurse further. So right, so if basically if the node doesn't exist, right, we want to create it, right, and if it does exist, then we want to recurse further with the node, but even before that, we'll have another else if. We'll say if node sub index and shorter dot length equals 0, right, then we want to stop. Right, there's nothing to do, so we want to stop, right? Else we want to recurse further. So if we were to call this right now, So you have PPLE, PP, and then P. So if we insert so let's just check if we can do this quickly. So we do I is less than word.length. We'll do I plus plus. We'll say console. We'll say let t equals word. We'll say t equals t dot substring starting at 1 going to t dot length. Then we'll print t. So PP, P, PP, P. So I'll add a T just to see exactly what's going on. So you have T, A, we have T, P, P, L, E. Console.log T, which is why this is strange. With Apple, right? Then we pop the first one off. It's I see. So maybe what we want to do is just a shortened version, which is just remove one character. All right, Apple, PPLE, PLE, LE. So this makes sense. So I think we just want to use this version. We can uncomment this and we'll say shorter, right? Word.substring. So we'll just remove that first character. So this should I see. And so we're going to do, if the node doesn't exist, we create it, right? And now, right, if shorter.length equals 0, right, else we want to depth first search even further. So we pass in Apple, right, to Dfs Insert, right, A does exist, we get the index, right, we shorten it, and then check if the node doesn't exist. It doesn't, so we create an n-ary tree, right, with word sub 0 as the value, right, and then we do short.length equals 0, and then we do this.dfs with the new node we just created. So we start at A, we create a new node at, so node sub index actually doesn't mean anything, since what we need is node, right, so children sub index, but nodes dot children, right, dot index. Then we do node, right, dot children sub index. So we want to recurse further, but we pretty much always want to do this other part, right? Because if shorter equals 0, then we stop, right? So that's the first thing we can do. Maybe we don't need this actually, since if word dot, so we'll say if node.children sub index, which would be index 0, right, for root, which is A. Does it exist? It doesn't, so we create a new n-ary tree for it with the word sub-0, which is A. Then we do a depth first search, starting at that index again with a shorter word. And actually, we don't have to do safe navigation because we already know this exists since it's pre-populated on node creation. So to search for a word, right, we can do Dfs search, right, and it'll take a node, which is going to be an n-ary tree, right? And a word is going to be a string, and search will call this.dfs search with this.root and word to lowercase. Then here we'll just do a depth first search. So if node, right, dot children, right, we have to calculate the index, right, it's going to be word, right, sub-0 dot car code at 0, right, minus 97. So if this index doesn't exist, and since we want to return a Boolean, actually we'll just do this. So if the node's children doesn't exist, right, then we want to return false, right? Otherwise, that means it does exist, right? So we want to create const shorter, which we'll just copy and paste from this line above, word.substring, right? And then we'll return this.dfs search, right? Node.children subindex with a shorter word. We do need a way to tie these all together, right? And if the node doesn't exist, right? But else if word.length equals 0, then we want to return true. Actually, no, we want to do true and depth first search even further. But if the node, we need to, when the word is empty, shorter.length equals 0, then we just want to return true by itself. So here we insert apple. Let's see if we can find apple. And it's not if shorter because that's the next word. We want to know if the current word is very small. If the current word is done, right, then we're done. Word sub-0. I see, right. So we want to know if the word even exists. So we're doing work here by calculating the index, but this only makes sense if word.length is not equal 0. Otherwise, if word.length equals 0, another way of writing this is just word.length equals 0, then we want equals 0, then we'll just assume that we can return true. Because that would mean if the word is empty, then that would be a good case. Then we can calculate our index, right, if the word isn't empty. And then we'd have if not children sub index, right? So if the child has never been created before, we return false, right? And in this case, we wouldn't need this anymore. Then we make it even shorter, and we say return true and depth first search with the shorter string and the child that we were interested in. So we insert apple, then search for apple, you get true. We search for app, you get true. Starts with app, returns true. Insert app, search app is true. So the only thing that's not true is insert search and starts with app. So you have insert apple, search apple, then search app returns true, but app does exist. They want us to return false. So app. So technically this should return true. So it starts with prefix. So it says starts with app, return true. Then we get to starts with here. Oh no, it should be search. So insert, search. So when I search for app, we actually return true. We're supposed to return false. Search app returns false. Even though A, P, it's unclear why it's starts with false. Returns true if there is a previously inserted string word that has the prefix. There is a previously inserted string word that has the prefix, but app does have the prefix for apple. Starts with app, search apple, search app. I guess we could also have a bit unclear here, but we could have a map, right? This would just be a map, and it wouldn't even be a map, it would just be a set of strings. And whenever we insert a word, if the word exists, we'll just do this dot map, and it's really a set. This dot set dot add word, and then starts with just returns true if there is a previously inserted string word that has the prefix, but app does have the prefix for apple and it returns false. Oh no, it returns the one we're failing insert search, so we're failing on search. So search returns true if the string word is in the trie, was inserted before. So we only know if it's been inserted before with the set. So we'll just say return this dot set dot has. This is unclear. Returns true if the string word is in the trie, was inserted before. That means we don't need to do DFS search anymore. say return this.set.has, and starts with, we can actually implement, might actually be the neat. So this should give us a passing test case, but we still have to fix right, and so here we just have to do a depth first search, right, because we didn't use the search for search, right? What we can go for here is to return DFS of starts with. So search will start with this dot root and do word or prefix dot to lowercase, and I think we should still get true. So I think that works. Tree data structure, which is used for retrieval of a key and data set of strings. There are various applications of this very efficient data structure, such as autocomplete, spell checker, IP routing, longest prefix matching, T9 predictive text, solving word games. Tries is used to solve boggle efficiently by pruning the search space. There are several data structures like balanced trees, hash tables, which give us the possibility to search for a word in a data set of strings. And why do we need try? Although hash table has constant time complexity for looking over a key, it's not efficient in the following operations: finding all keys with a common prefix, enumerating a data set of strings in lexicographical order. Another reason why try outforms of hash tables is that as a hash table increases in size, lots of hash collisions and the search time complexity would deteriorate to linear time. Where n is the number of keys inserted, try could use less space compared to hash table, storing many keys with the same prefix. In this case, using try has only O of m time complexity, where m is the key length. Searching for a key in a balanced tree costs OM log n time complexity. Tree is a rooted tree. Its nodes have the following fields: maximum of R links to its children. Each link corresponds to one of the R character values from the dataset alphabet. This article, we assume that R is 26, number of lowercase Latin letters. Boolean field, which describes what the node corresponds to the node of the key. Specifies whether the node corresponds to the end of the key or is just a key prefix. Of a key leet in a try LEET is n true. So we have tree node, which is R links to node children, so it's a tree node. Links equals new try node R, which is 26. Contains key links of character minus a does not equal null. We do tree node get character links. We could have just subtracted it by the ASCII value of a as well. To put, we'll do links of car minus a equals node, void set end is end equals true. Most common operations in try are insertion of a key and search for a key. We insert a key by searching into the try. Start from the root and search for link, which corresponds to the first character. There are two cases a link exists. Inserting LE into the tree. Root LE, end of key. Inserting LEET, already exists. Then we create E and T. Then we can insert code. We repeat this step until we encounter the last character of the key. Then we mark the current node as an end node and the algorithm finishes. So insertion node equals node dot get. I see, that's one way to do it. You don't have to calculate the index this way. Search for a key in a trie. Each key is represented in the trie as a path from the root to the internal node, or leaf. Start from the root with the first character. Examine the current node for a link corresponding to the key character. There are two cases. Link exists, move to the next node in the path, follow this link, and proceed searching for the next character. A link does not exist if there are no available key characters and the current node is marked is end. We return true. Otherwise, there are two possible cases in which each of them return false. There are key characters left, but it is impossible to follow the key path in the trie, and the key is missing. No key characters left, but the current node is not marked as is end. So ours was, if the word is empty, we did good. If the node doesn't exist, we return false.